is similar to what we did in lesson 5.4. We're going to look at some properties of some special types of parallelograms. So in section 5.4, we talked specifically just about properties of parallelograms in general. In this lesson, we are going to take a look at rectangles, rhombuses, and squares. So, and you don't need to do the launch activity right now. We are going to skip that for this lesson. And again, we're going to spend some time looking at the properties of rhombuses, rectangles, and squares, which we're going to say are special parallelograms due to just the nature of these shapes. So first of all, in this first investigation, the best way to do this online is to just to go over this picture that they have here. So essentially what you would do to complete this investigation is you would take a ruler and you would draw a picture of your ruler, or you would lay your ruler down on your paper and you would trace over it and draw lines down the side of the ruler. Those two lines, since they are the sides of a ruler, are parallel. Then you would take the ruler and you would adjust the position of the ruler on your paper to draw two more lines on your paper that are parallel. Again, by tracing the sides of the ruler. And what you would notice is if you took your ruler and measured the sides of this shape that are created, you would find out that this side is the same length as this side over here. So this side and this side and this side and this side would all be congruent. And so what we have here is this shape is a four-sided shape, quadrilateral, with two sets of parallel sides, and all the sides of that shape are congruent. So what we come up with is this conjecture about a double-edged, straight-edge conjecture, which says if two parallel lines are intersected by a second pair of parallel lines that are the same distance apart as the first pair, then the parallelogram formed is a rhombus. Okay, so again, what that's saying is if you have a pair of parallel lines that are intersected by a second pair of parallel lines and both pairs of the lines are the same distance apart, then you get a rhombus, which leads us into our discussion of the properties of rhombuses. So again, quick refresher, a rhombus is a parallelogram with four congruent sides. And so what we're going to do is we're going to take a look at what special properties we have of rhombuses. So what we're going to do is we're going to take a look at a Desmos slide. And so we have this rhombus here, and what we're going to do is we're going to construct diagonals AC and DB. So if we construct diagonals AC and DB, we get something that looks like this. And we're going to label their point of intersection as point M. And so we'll label this point M. And what we're going to do is we're going to make some observations here. So the first observation, if you're looking at your notes, states that it has something to do with the diagonals of the rhombus. So if we look at the diagonals of this rhombus, some measurements that we might want to take a look at some of the measurements. So remember in the previous lessons we saw that a number of diagonals bisected each other. So if we look at, actually we have to construct a few more segments here. So if we trace over these segments here, we have AM, we have MC, we have DM, and we have MB. So if we look at these and we take a look at the measurements, 4.47, 4.47. And the measurements of this, 2.24, and the measurement of this side would be 2.24. And what you notice is that the measurement from AM to MC are equal. They're both 4.47. And the measurements from DM to MB are both equal. So they, they appear to bisect each other. All right. So if we're looking at our notes, it says the diagonals of a rhombus are blank and they blank. So what we're going to do is we're going to say, based on these observations that we have, these diagonals appear to bisect each other. So we're going to say, and they bisect each other. And now we got to figure out the next part of this conjecture. And so I wrote that there because grammatically it wouldn't make sense if we wrote it in that first blank. So the second thing we're going to take a look at is, let's take a look at how these diagonals intersect. So if we take a look at that, oftentimes we might wonder, are these diagonals perpendicular to each other? So if we look at the angle DMC, you'll notice that it does measure 90 degrees. And so if that angle measures 90 degrees, then we know that each of these other angles measure 90 degrees. And if two lines intersect at a 90-degree angle, we know that they are perpendicular. So we know that the diagonals of a rhombus are perpendicular as well. So when you're looking at a rhombus, you know that the diagonals of a rhombus are perpendicular and they bisect each other. Now, the next thing that we're going to look at is the angles. Okay, so there's something going on with the angles of a rhombus. So let's go back to this, and we're going to clear out all this. We're going to draw in our diagonals AC and DB. And then let's go ahead, and if we look at this, it says measure the angle CDM. And again, our point in the middle is point M. So if we measure this angle CDM, we have CDM. Let's also measure MDA or MAD or ADM. So if you look at this, you should notice that, hey, angle D appears to be bisected by this diagonal. I got 63 degrees and 63 degrees. Let's take a look at angle DCM and angle BCM. If you take a look at that, it appears that both those angles are bisected as well. And so if we were to go about and measure ABM and CBM and BAM and DAM, we would notice that those angles would also be bisected. So what we notice about a rhombus is that the diagonals of a rhombus bisect the angles of the rhombus. And you might recall that the same type of thing happened for the vertex angles of a kite. Again, this is a special type of parallelogram or a special type of quadrilateral where all the angles are bisected by the diagonal. So what we have here is that the diagonals of a rhombus bisect the angles of the rhombus. Now, at this point, we have made some conjectures about a rhombus, a quadrilateral with 4 congruent sides. Now what we're going to do is we're going to look at a quadrilateral that has 4 congruent angles. And that shape that we're going to look at is a rectangle. So again, a rectangle is a parallelogram with 4 congruent angles. All the opposite sides are congruent, but not all of the sides like they were in a rhombus. So what we're going to do is we're going to take a look at a rectangle. And what we're going to do is, if you are looking at your notes, you'll see that our conjecture that we have is based on the diagonals. So let's take a look at this. What we are going to notice here is after we draw our diagonals, we have diagonal AC and a diagonal DB. And then we're going to put point M in here. So point M. So what we notice is we want to take a look at our diagonals here. What do we notice? So some things that we've taken a look at is, we've noticed in the past that some diagonals bisect each other. We've noticed that some diagonals are perpendicular to each other. We've noticed some diagonals are congruent to each other. So let's take a look at what we find when we measure these diagonals. So we have the diagonal AC that's broken up into AM and MC. We have the diagonal DB that is broken up into DM and MB. And so if you take a look at this, you should notice 2 things about the lengths of the diagonals. First of all, this length from D to B is 6.52 plus 6.52. Okay? The length from A to C is 6.52 plus 6.52. Again, so if you look at that, you should notice that the diagonals are congruent. Also, you'll notice that the length from DM is equal to the length of MB, which tells you that this diagonal is bisected, because bisected means broken up into two equal pieces. And also, you'll notice that AM is congruent to MC, therefore AC is also bisected. So what that tells us is that the diagonals of a rectangle are 1, congruent, and 2, they bisect each other. Okay. Now, what we're going to do last is we're going to look at squares. Okay, and we're going to kind of look at squares without, without looking at a picture, right? Without using Desmos. But what I want to do before we attempt this is I want to go back to this diagram right here. And what you'll see about this diagram is you'll see that in this Venn diagram, we have the word parallelograms. All three of these shapes that we're talking about, squares, rhombuses, and rectangles, are parallelograms. And inside of this Venn diagram, you'll notice that there's an overlapping region. And so what does this diagram tell us? All right, well, first of all, it tells us that squares are rhombuses and rectangles. Okay, because squares are the section for squares. It is in the overlapping portion of rectangles and rhombuses. So what does this mean? Okay, what this means is that squares share all the properties of both rhombuses and rectangles. So whatever properties we found about rhombuses and whatever properties we found about rectangles is true for squares. Okay, so if we know that, then we know that a square shares all of the properties that we just found for both of those shapes' diagonals. Okay. Now, on top of that, a square is a parallelogram, and it's a rectangle, and it's a rhombus. So the square has the properties of all three of those shapes. So to refresh our memories on parallelograms, we know in parallelograms that opposite angles are congruent. We know corresponding angles are supplementary. We know that opposite sides are congruent, and we know that diagonals bisect each other. So if we take all four of those and combine that with what we just saw about rectangles and rhombuses, what we would find out is that the diagonals of a square are congruent. They are perpendicular. And they bisect each other. Okay. Now, moving into these different proofs, what we're going to do is we're going to walk through two flowchart proofs. The flowcharts are already created. There's just some blanks that we have to fill in for the reasonings. So this first proof is going to demonstrate logically that if a quadrilateral has four congruent sides, then it is a parallelogram. And then if it is a parallelogram with four congruent sides, it is a rhombus. So again, what we're going to show is that if a parallelogram has four congruent sides, then it is a rhombus. Okay? So let's take a look at this. We're given that quadrilateral QAD has QU congruent to UA, congruent to AD, congruent to DQ with diagonal DU. We want to show that this shape over here is a rhombus, meaning a shape with four congruent sides. So if we take a look at this, the first box says QU is congruent to AD. QU, AD. That's true because it's given to us. QD and AU. QD is right here, and AU is right here. Are they congruent to each other? Yes. Why? Because it's given to us. And finally, we have DU is congruent to DU because it is the same segment. we know that this diagonal right here is equal to that is equal to itself. Now, what you should notice there is that it creates two triangles. All right. Again, we have QU is congruent to AD, and then we have QD is congruent to AU. All right. And they're all congruent to each other, so they all have the same congruency markings on it. Now, we also know that this side is congruent to itself. So what we have here is we have a side-side-side congruence conjecture. So we're able to say that those two triangles are congruent to each other because of the side-side-side congruence conjecture. Now, based off of that conjecture, we're able to say that angle 1 is congruent to angle 2 and angle 3 is congruent to angle 4, and that is based off of CPCTC. Now, that leads us to being able to say that QU is parallel to AD. So we're saying now that QU is parallel to AD. And we're also saying that QD is parallel to AU. And we're allowed to say that because that is the converse of the parallel lines conjecture. All right. Remember, the parallel lines conjecture said that if two lines are parallel and are cut by a transversal, that the alternate interior angles are congruent. Now, we know the alternate interior angles are congruent here, so we're able to say that those two lines are parallel. Now, because we're able to say that opposite sides are parallel, we can say that QUAD is a parallelogram because that's the definition of a parallelogram. Now, we're also given that all four sides are congruent. The definition of a parallelogram, so that definition of a parallelogram, given that all four of these sides are congruent, leads us to say that QUAD is a rhombus because that is the definition of a rhombus. Okay, and that is a general proof of, oops, and I forgot to share my screen back. So that is the general proof of showing that this is a quadrilateral that is a parallelogram with four congruent sides is a rhombus. Okay, and I forgot to share that screen back, so I'll pause here for a second while you write down what we had. Again, we used what we were given, and we're able to show that these two triangles that we have over here were congruent using the side-side-side congruence conjecture, which then allowed us to show that these angles 1 and 2 and 3 and 4 were congruent because of CPCTC. And then we were able to say that because we know that those angles are congruent, then we're able to say that these sides are parallel because it's the converse of the parallel lines conjecture, which then leads us to say it's a parallelogram with four equal sides, which is the definition of a rhombus. Now, the second proof that we're going to look at is to look at where we have, if we have a parallelogram with four congruent angles, we want to prove that it is a rectangle. Okay? So again, we have this quadrilateral ABCD with angle 1, 2, 3, and 4. Those are all congruent angles with side AD extended to form angle 5. All right. So the first thing that we're given is that the measurements of all four angles are congruent. That is given to us. Now, because this is a quadrilateral, we know that the sum of the interior angles is 360 degrees. Because of that, and since all four angles are congruent, that means that all four angles would have to equal 90 degrees. That's the definition of congruent angles. Now, what we also have is that, so we kind of just skipped over and said this right here. This right here is what allows us to say that the sum is 360 degrees. Okay, so this is the quadrilateral sum conjecture. Okay, and then what this leads to with us having this definition of congruent angles is that we can say angle 5 is congruent to angle 3, and we can say angle 5 is congruent to angle 1. That's just basic substitution of algebraic operations. And what we know is the measurement of angle 4 is congruent to the measurement of angle, or plus the measurement of angle 5 is 180 degrees. and that is the linear pair conjecture. Now, with this, we know that the measurement of angle 4 is equal to 90 degrees. So we have 90 plus angle 5 is equal to 180. That means that angle 5 has to be equal to 90 degrees. So we're able to substitute that in and say that angle 5 is congruent to angle 1. Now, what we are doing next is that we can say that these lines are parallel. We know that AD is parallel to BC. And we know that AB is parallel to CD. And the reason that we can say that is, again, the converse of the parallel lines conjecture. Okay, we used alternate interior angles to prove that those lines were parallel. Now, after that, because the opposite sides are parallel, we know that ABCD is a parallelogram. That is the definition of a parallelogram. All right, and finally, because all 4 angles are congruent, we know that ABCD is a rectangle, because a rectangle is an equiangular parallelogram. So this is the definition of an equiangular parallelogram. All right. So again, you won't be asked to do many proofs, but those are just some basic flowchart proofs that show that in fact a parallelogram with 4 congruent angles is a rectangle, and a parallelogram with 4 congruent sides is a rhombus. The last thing we're going to look at is an example of just using the properties that we talked about to find some missing measurements of angles in this problem. So it says find the measurements of angle X, Y, and Z. Describe your reasoning for each measure. So X, Y, and Z. So, we'll describe this verbally. So if we take a look at this, we know that diagonals are congruent in a rectangle. We also know that diagonals bisect each other in a rectangle. So again, we know that the diagonals bisect each other in a rectangle. Now, because of that means that we know this is congruent to this. We know this is congruent to this. And so what we see here is we have a bunch of isosceles triangles. This triangle DEC is isosceles. So because it's isosceles, we know that this angle over here has to also be 22 degrees because base angles of isosceles triangles are congruent. So we have 180 minus 22 minus 22, which gives you 136. So we know angle E is equal to 136 degrees. Now, angle E, knowing that's 136 degrees, allows us to find both angle X and angle Z. Angle Z is going to be equal to 136 degrees because that is a vertical angle. Okay, that's the vertical angle conjecture. And then angle X is going to be equal to 180 minus 36. And that's going to be, if I could type it in correctly, 44 degrees. Okay, so angle X is going to be equal to 44 degrees. And the reason we know that is because it is a linear pair with angle Z and E. Okay, now finally, with angle Y, again, we know that this triangle A, Z or E or whatever you want to call it, D, AED, is an isosceles triangle. Now, because it's an isosceles triangle, again, we know that the base angles should be congruent. We know that the triangle sum conjecture has 180 total degrees minus the 44 for angle X. And that leaves us with 136 degrees to be split among the two base angles, which gives us Y is equal to 68 degrees. So again, you're going to complete your homework. If you have any questions on this, make sure you message me on Remind or email or ask at the beginning of the next class.